Well, today we're going to do an experiment which actually utilizes a number of principles from the world of physics. And let me try to tell you what we need and explain some of the principles briefly. I have a little desktop toy here, sometimes called Newton's Cradle, and you can buy these again online. Just go on, do a Google search for Newton's Cradle, or go into a science center store or someplace like that, and you will no doubt find these on display and for sale. So we need Newton's Cradle. The other thing I have here are 3 chromium steel balls. They can be they're magnetic materials, so magnets will stick to them. In fact, I think that this is pretty much the same material that the larger balls of the Newton's Cradle are made of, except these are smaller. And I have a rare earth disk magnet, which is one of my standard tools for doing these experiments with electricity and magnetism. First, let me demonstrate for you the idea here behind the Newton's Cradle, and then show you a neat little experiment with the magnet. Well, Newton's Cradle here it's called Newton's Cradle because it's used to illustrate the Newton's concept of conservation of momentum. And that as I pull one of the steel balls back here and let it go, there is a wave generated, actually a mechanical wave generated through the steel balls that passes from one ball to another, moving at the speed of sound until it gets to the last ball, hits the last ball. There's not another ball here for it to transfer the energy and momentum to, so the last ball then flies out. And according to Newton, in an ideal situation, it would have exactly the same momentum that this ball had when it struck. Now, in actuality, it loses a little bit. Just the sound, if you like, carries energy away from the system, so that as this thing bounces back and forth, it loses a little bit of energy, a little bit of momentum on each bounce, and gradually will slow down and stop. But it's a pretty neat illustration of the concept of conservation of momentum, which you can also see with billiard balls and lots of other car accidents and such. Oh, let me just show you some of the neat things that you can do with this Newton Cradle before I move it aside. Is that you move 2 balls up. Watch what happens. I think the neat thing is moving 3 balls. Here, now watch this. I move 3 balls up. So all sorts of neat little things you can do with Newton's Cradle, and for the science geek, it never loses its fascination. Okay, now here we have our steel balls and our rare earth disk magnet. Let me get 2 disk magnets here together. So I have 2 rare earth disk magnets. Of course, once I stick these together, it takes Superman to pull them apart. So here I have 2 steel balls stuck to 2 disk magnets. Now as I take this 3rd steel ball and I move it close into the disk magnet, let me explain what's going to happen. Well, let's not. Let me first do it, and then I'll explain what happened. So I'll put this like here, just sit on the table just like that. And I'll look very closely, because I'm just going to move this 3rd steel ball up and I'm going to let it go. I'm going to slow this down now. Okay, well, what's happening with that? Well, we have a little bit of Newton's Cradle. We have a little bit of kinetic and potential energy, and there's a fair amount of science going on here. First of all, from the Newton's cradle aspect, that as soon as this steel ball strikes the two magnets like that, we generate a energy wave going through the magnets, through the first steel ball, and it's the second steel ball. Now there's a relatively weak magnetic field holding the second steel ball onto the magnets. It's certainly weak compared to the two that are actually touching the magnet. So it launches this steel ball off because of Newton's conservation of momentum. Now, where does all this energy and momentum come from? Because when I pull this ball away from the magnets, what I'm doing is I'm giving this ball potential energy with respect to the magnetic field. Now, when I let it go, that potential energy converts to kinetic energy as the ball falls toward the magnets. And that's where the energy comes from. Now, what did I do with the original Newton's cradle? There's no magnetic field here. The field here is gravity. As I pull this ball up like this, as I give the ball height above the other four balls, I give it potential energy in the gravitational field. And then as I let it go, gravity pulls on it, converts that potential energy into kinetic energy, and starts the Newton cradle into going. So this concept of kinetic energy and potential energy also works with the magnetic fields. Again, what I'm doing here, when I pull this ball off of the magnets, I'm giving it potential energy with respect to the magnetic field. Then when I let it go, it falls, just like falling in gravity, converting that into kinetic energy and then launching that ball off according to Newton's law of conservation of momentum. So that's a neat little experiment. Two rare earth disk magnets seems to work fine. You can probably also make it work with one. Let's see if we can do that. Oh, there it worked. Seemed to work pretty good. Yeah, it works even with one. Of course, the stronger the magnetic field, the faster this ball will strike the magnets. And this speed, it's this speed right in here, which is, we need that to be fast in order to launch this ball off the end. But that's our experiment, and hope you enjoyed it. You carry this around in your pocket all day long and show it to people. I do. I'll see you next time.